Right, you guys, we are on to 2.8. Let me jump over to the lecture. Finally, we have enough behind us where we can now define the derivative. Let's go for it. Here's where we left off in 2.7, the derivative of f of x at a. And we created this new formula involving h. We said the derivative of f of x at a, the notation is f prime of a equals the limit as h approaches 0 for f of a plus h minus f of a all over h. We recognized at that time, this is actually really similar to the difference quotient, right? It just has an a in the place of where we would normally see an x. But a is an x value. So what is the definition of the derivative? Here's what we're going to do. The definition of the derivative is simply a matter of replacing the a's with the variable x. Everything else is the same. So now we're going to call it f prime of x equals the limit as h approaches 0 for f of x plus h minus f of x all over h. And there's our difference quotient with the limit as h approaches 0 in front. So what happened here? What we were doing in 2.7, we could only find the derivative at one particular x value at a time. So whenever we had a function, it had to tell us the value of a where we were to find that derivative or the slope of that tangent line. Now we're generalizing it, we're abstracting it. We're saying we don't need to know a specific value of a, we're just going to leave it as a variable x. And so all of the a's become x's. Why is that better than having a specific value every time? And here's this note at the bottom. F prime of x is now a function. We're not finding the derivative of any one particular spot. We're finding it in general. We're finding a formula for it. F prime of x is a function that will then give us the derivative at any x value. Once we know what f prime of x equals, and that'll be, as it says, a function, so this will be some kind of an expression in terms of x, we can then plug in x values and figure out the derivative at any place that we like. Okay, so we're going to take a look at some examples. We'll see how this plays out. And if you're like, what does he mean? It's a function or anything? Okay, we're going to see it here. So these first two, we had done these same functions back in 2.7, where we found derivatives at particular values. We're also going to add on another one. So we'll see exactly how much we can get through in this video. We might carry it on to another one. I'm not sure. But okay, let's go for it. I'm going to switch cameras. Example, find the derivative function. F of x equals x squared plus 2x minus 1. Okay, let's do it for this one. Let me write our formula, f prime of x, the limit as h approaches 0, f of x plus h minus f of x all over h. Okay, so essentially we're going to set up the difference quotient. We're going to simplify it. And hopefully after simplifying the difference quotient for our function, we'll be able to plug in h equals 0. We'll have already canceled out h's and that sort of thing. We'll be able to plug it in and we'll get a function to describe our derivative. Let me do the f of x plus h just kind of to the side, kind of like to do that. So here that'd be x plus h squared plus 2 times x plus h minus 1. X squared plus 2xh plus h squared plus 2x plus 2h minus 1. Okay, so that whole thing is going to go in. limit as h approaches 0, x squared plus 2xh plus h squared plus 2x plus 2h minus 1 minus, we're going to subtract the original function. And it's all over h. Okay, if we've had some practice with difference quotients, hey, this feels very familiar. Well, from here, let's see, x squareds cancel out. 2x minus 2x, -1 minus -1. And we've got 2xh plus h squared plus 2h over h. We can then factor out an h. H times 2x plus h plus 2. Cancel out the h's. Limit as h approaches 0 for 2x plus h plus 2. Finally, at this point, we can now plug in 0 for h, and we have it, 2x plus 2. There's our answer. You can see, yeah, it's an expression involving x, so that's going to work just like a function. Interesting. So you'd say, okay, like, how was this helpful? All right, so what if at this point, we kind of go a little bit further, just kind of in our investigation. What if we wanted to know, what is f prime of 3? That's what we did in the previous section. We found this. We'd say, well, once I know this formula, right, f prime 3, well, that's 2 times 3 plus 2. And guess what? F prime of 3 equals 8, which is what we found before. Like, okay, well, we were doing this already. Sure, but now we could figure it out for other values of x very quickly, right? Like, what is, right, f prime of, I don't know, -7. I don't have to do a whole new question and do all this work basically again from scratch. I can go right here and say, well, f prime -7 is 2 times -7 plus 2. So f prime -7, what would that be? -14 plus 2, -12. And right away, boom, I got it. And I could do that for any x value. Immediately, I can know the slopes of tangent lines, anywhere I like. Okay, very cool. Hey, what about, there's one kind of interesting one. What about f prime -1? What's interesting about that? F prime -1, 2 times -1 plus 2. Okay, that would equal 0. Why is that interesting? Oh man, okay, we just got to graph this really quick. Graph our function x squared plus 2x minus 1. There it is. Let me give it a different color. Really pop off the page. Okay. So we know at 3, 3's kind of off, kind of up here someplace. Way up there. There it is at about 14, I think. Okay, we know the slope there is 8. -7. Okay, that's back here. That's much higher. That slope was -12. The 0 here at -1. Wow, that's right at the very bottom of the curve. Why would it be that the slope of the tangent line is 0? What would the tangent line be doing right there? Well, if it's the point at the very bottom of the parabola, wouldn't the tangent line be a horizontal line that just kind of grazes past right there? Well, the slope of that horizontal line would be 0. Interesting. Okay. Just kind of a nifty thing to point out. Let's do another one. Part B. Let's have the square root f of x equals square root 2x plus 3. Interesting. Okay. So our formula, the limit as h approaches 0, f of x plus h minus f of x all over h. Let's see here. So f of x plus h, 2 times x plus h plus 3. That's going to be 2x plus 2h plus 3. So setting this up, limit 2x plus 2h plus 3 minus square root 2x plus 3 all over h. Well, as we suspect, we're going to have to multiply by a conjugate here. Conjugate of our numerator. Two square roots involved in that conjugate. No problem. Let's see if we FOIL this times this is simply 2x plus 2h plus 3. The outside and the inside going to cancel out, and then we'll have this times that. Be careful here when those multiply, it's negative, but that negative needs to distribute to the 2x and the 3, and then over, and this we're going to leave factored. Like so. Okay. Once we have that conjugate, right, it looks like a mess, but it's going to clean up so good. The 2x's cancel, 3 minus 3. And then finally, those h's cancel out as well. So we got 2 over square root 2x plus 2h plus 3 plus square root 2x plus 3. And now finally, I'm going to plug in h equals 0. So I don't need to write, or I should not write the limit as h approaches 0 any longer. When that goes in, notice that 0, that's going to go away completely. And what will it be? Square root 2x plus 3 plus square root 2x plus 3. Let's write it all out. All right. So there'll be 2 of them. We can even cancel out the 2. Interesting. Wow. Really simplifies down. That, look at that. Look how simple that is in the end. Who would have guessed, right? The original and the derivative is 1 over, okay. This really simplified nicely. I think some of the details of the 2's, it might not always work out this well for square roots, but here, wow, that's pretty sweet. Okay, what was it that we did before? We had found f prime of 11, right? Last section. So what would that be if we plug in 11, 22, 25, 1/5? Yeah. You know, obviously here we could explore more. We could plug in other numbers. There you go. So wherever we want to find the slope of that tangent line, hey, plug it into this, boom, done, got it. Okay, one more. Let's squeeze it in. Part C, g of x equals 1 minus x over 1 plus x. Now this is a little different. We got the fraction, right? Let's see here. What would it be for g of x plus h? Let's just go right to that. 1 minus x plus h over 1 plus x plus h. Replacing both the x's. In the numerator, those parentheses matter because that minus sign distributes. In the denominator, not so much. So g prime of x equals the limit as h approaches 0. This whole thing minus the original g, and that is all over h. Okay, wow, yeah, those fractions can be a beast. Here's what we want to do. Here's what I'd recommend. Just focus on the numerator for the moment. Let's simplify just this part of it. Then we'll go back in and plug it all back, and clean it up. Here's what we want to do with that numerator. Get a common denominator between the two fractions. And then we'll just kind of see what happens there. This common denominator, you kind of look at it and you're like, well, 1 plus x plus h and 1 plus x, like, do they have 1 plus x in common? Actually, no. Because we're adding the h, we have to think of these denominators as completely separate factors. So to get a common denominator, we're going to say for this one, we need to multiply by 1 plus x. And for this one, we need to multiply by 1 plus x plus h. And then that's all going to be over the two of them together. And hopefully that's not, hopefully that's clear enough. So we got this one times this denominator over that, minus this one and that denominator, and they're both over the same. Okay. We've got a lot of distributing to do and then canceling out of terms. So starting with this, let's distribute everything. 1 plus x negative x minus x squared minus h minus xh. I'm going to put that in parentheses because that's like the first part, minus, because we're subtracting this, be careful, use parentheses, and then we'll distribute everything. 1 plus x plus h minus x squared minus xh. And that is all over our same common denominator. There. I think it's going to clean up really well. We're going to be able to see the cancellation. 1 minus 1, x minus x, negative x minus negative x squared minus negative x squared. That's all gone. Even negative xh minus negative xh. The h's don't cancel because this one's negative, this one's positive. So negative h minus h is negative 2h over our common denominator. Okay. So all of that numerator's simplified here. Perfect. Let's pick it up from there. The limit as h approaches 0, I've got negative 2h over 1 plus x plus h, 1 plus x, and that's all over h again. Here's what we can do. We've got a fraction over something else. We'd like to make this just one fraction, one numerator, one denominator. Here's how we can do it. Think of this as h over 1. And then we'll flip and multiply. may remember this nifty algebra trick. Flip that h over 1 to 1 over h, and then what do you know? Boom, h's cancel. G prime of x equals the limit as h approaches 0. Canceling that h out was the key. And now finally, with the h gone, we can plug in the 0. And this one's actually cleans up really well too. Look at that. We put in 0 and it's just 1 plus x times 1 plus x, negative 2 over 1 plus x squared. We got it. You know, of course, so here, same idea. We could plug in any value of x and figure out the slope of the tangent line there. There is one value of x here that's noteworthy. What about x equals negative 1? You think, well, if you tried to find g prime negative 1, I mean, any other x value is going to be fine. You'll get a number, but negative 1, you're going to get negative 2 over 0. So that's a DNE. That derivative would not exist. You're like, why? What's up with that? Is it possible that a derivative might not exist at certain x values? Here it makes a lot of sense why. I mean, think about the original function. What's happening at negative 1 in the original function? Well, you're dividing by 0 there as well. Notice that g of negative 1 is undefined. So that's not even, it wasn't even in the domain in the first place. In fact, right, think g of x, I'll just write it again here, x minus 1 over 1 plus x. It has a vertical asymptote at negative 1. So yeah, I mean, if there's a vertical asymptote at negative 1, certainly the derivative can't exist there. And it works out that way. It's just right there, like in the function, like, yep, negative 1, not going to work. Well, you know, so that's, I got to graph this. Okay, really fast. Let's try it out. 1 minus x over 1 plus x. Yeah, so that vertical asymptote at negative 1, certainly the derivative won't exist there, and it works out that way in the formula. Pretty nifty. So it's not even that we have to like remember it. It's just there for us. We can't do it even if we wanted to. Okay, you guys, we definitely have done enough in this video. Continue the conversation in the next one.